Today's short video, let's solve Rosalind's bioinformatics stronghold's fourth challenge, rabbits and recurrence relations. And of course, this problem contains more background information than before, based on these problem statement. And then if you click this part, again, more background information, feel free to read that. But in this case, I'm just going to start off reading in this part of the section, and then get into the conceptual approach. When finding the nth term of a sequence defined by a recurrence relation, we can simply use the recurrence relation to generate terms for progressively larger values of n. This problem introduces us to the computational technique of dynamic programming, which is important, right? Which successively builds up solutions by using the answers to smaller cases. Given positive integers of n less than or equals to 40 and k less than or equals to 5, return the total number of rabbit pairs that will be present after n months. If we begin with one pair and in each generation, every pair of reproduction age rabbits produces a litter of k rabbit pairs instead of only one pair. Sample dataset 5.3, sample output 19. So the basic premise of this problem is basically just a modified approach of sort of the classic rabbit Fibonacci problem. Like previously mentioned, this Rosalind problem is basically just a modified version of the classic Fibonacci rabbits. Right, and instead of writing out the notes, in this case, I think it was best to sort of represent it visually and graphically. And in this first sort of graphic, this sort of tracks it numerically, which is great, based on this table right here. And of course, these rabbits is depicted. But then I think this one sort of best represents, what exactly it sort of represents and how you would sort of think about this particular problem, solving it using a dynamic programming approach, right, as required by the problem, I'd say. So in this case, as mentioned by the problem, we start with one pair in generation, but keep in mind that first pair is actually young rabbits, which can't technically reproduce. And what happens is that in the next coming month, they become adult rabbits, and in this case, they actually can reproduce and only doing one pair. Right, because we're explaining the classic rabbit problem, and then this previous generation moves to the next generation and reproduces another offspring, but then in this case that offspring that was reproduced by these original rabbits then becomes sort of adults and follows the same general pattern. But then keep in mind, again, this only reproduces one sort of offspring, and based on this k, we'll then sort of have to manipulate the sort of function in which we'll sort of apply that specific little rabbit factor. The programming language that is used to solve this particular problem is Python, and the programming platform is Replit. But feel free to use any language, any platform, because technically the only thing that Rosalind does ask of you is the fact that when you submit the solution, it has to follow the same general format. So again, this is sort of taken from the problem, which is the sample input, 5, which is equals to the number of months. This is the number of litter pairs. Sample output is the sort of number of pairs at that given month, which is 5, right? So now we're going to actually write a function called rabbit Fibonacci, right? So it's going to pass in that number of months, and then k, which is going to be sort of that litter factor, right? And then before we write out that entire function, let's actually create two specific variables that we're going to be passing onto that function. And with that specific rabbit Fibonacci function, what's going to happen is we're actually going to return an entire dynamic programming array. And it's important to keep in mind that the main feature of dynamic programming is actually the fact that you're sort of using more memory in order to sort of reduce the calculation costs in this case, right? So we're passing that, and then we're simply just going to print the specific value to be expected at that given month, right? Perfect. So now, and then again, since we are using that extra space, we're going to write a dynamic programming array to store all our values. This way, if we are, so let's say, in this case, let's say 5, but if we wanted to know at month 3 how many was there available, we can essentially just access that given index. I'll just explain more later on. So now, considering this is the Fibonacci sequence, of course, it's important to note that at that first index is always going to be 0 and then 1. This way, we're sort of maintaining or making sure that we're actually making sure that the natural counting values that we're going to be using, right? Because otherwise, if let's say, you know, based on that previous diagram is shown here, if you say that first index is going to be equal to 1 and then 1, what's going to happen is that it's going to return sort of the wrong month in this case. Or unless, I mean, you can technically sort of refactor that again. So now let's just write a for in range loop, which just starts off appending into the dynamic program array at index 2 and then stops at n plus 1. So in this case, it's not going to iterate through the entire, well, n equals 6, it's going to stop at n equals 5, right? And then you're just simply appending that. And then again, main feature of the Fibonacci sequence is the fact that you're technically adding, you know, the previous sort of value together to make a new, or yeah, make a new value. So let's see, right? And then give me one moment, and then I'll explain later on what's technically happening in this problem. All right, let's see. Then we're just going to make sure, right, in this case, keep in mind, we're actually returning that entire DP array, but we can obviously return just that specific month to output. But yeah, so basically what's happening here is that since we're already inputting values at 0, which is at first index, which is 0, and then 1, we're simply just starting off at index 2, and then ending at k minus 1 in this case, right? So in this case, for example, let's say at index 2, what's going to happen? It's going to be 1 as well, because you're adding 0 times k, which is still going to be 0, and then add 1, so it's going to be 1 at that second, so it's going to be 0, 1, 1. And then on the next one, what's going to happen is going to be, you're going to be adding sort of 1, and then times 3, so it's going to be 1 times 3, which is I minus 2, it's going to be 4, and so forth. So now, if we say that we run this particular problem, it's going to show us, okay, perfect, it's going to output 19. So this is simply download the data set. And then what we're going to do is simply going to open that txt file and then just copy that into Replit. And again, you can refactor the code to sort of make sure you're actually sort of reading a txt file instead. But in this case, I'm simply just copying and pasting. 2, so this should give us the answer. So the answer for this particular case, I mean, again, this is random. Just simply copy and cut that into Replit. Okay, submit that, and it should output. There you go. And before we let you go, what's going to happen is I'll quickly explain again. There's that trade-off that does exist, and in this case, the time complexity is going to be O(n). The reason being it's linear is because there are a number of times we're sort of adding and then appending to the array. Completely depends on the number of months that's sort of expected to calculate. And then the space complexity is going to be O(n) as well, considering that we are sort of storing it in a DP array. And then, yeah, we're returning that